All right. So what we know so far is how to calculate derivatives and how to calculate integrals. So if we have a scenario where either of these could be used, I guess there should be a y here. It's just not an integral of 1, so it's integral of y. But either way, we know these and we can solve a good number of integrals with them. There's still some tricks that we will develop as we try some problems that involve these, but I want to do an overview. Let's title this Overview of Calculus Applications. I won't go in complete depth. Overview of calculus applications. So I won't go in complete depth, but I really want us to get a feel for what these are. You know? I guess you can't answer that. All right. So what can you do with the derivative? So let's graph a function. All right, that's going to be a random function. And now let's graph its derivative right under it in orange. And before we continue, let's draw axes so we know what to talk about. So there's going to be an axis. Let's make a line here. Let's carry this line down. Then we have another axis. We're going to do this like we kind of did some cosine drawings. All right, so now let's graph the derivative in orange. And so it begins after this line. So how do we graph it? Well, right here we have a negative, so I know it's going to be some kind of negative zone. It's kind of flat here, so I'm going to say 0. Kind of flat here, so 0. Looks kind of. Wait, that's positive, not negative. Wait, yeah, it is negative. Then that's positive over here. How about at 0? What was it equal? That's kind of a negative. No, that's a positive. It's going like this. So it's a positive. So let's give it up here. Yeah, it's positive going down. So I'm thinking, let's try to connect this with a continuous line. Not perfect, but I'm seeing a parabola here. Now my line was weird and kind of wonky from the get-go, but I think you're getting the idea. All right, so this is the derivative. If this is f of x, this is our f prime of x. So what can we do with that? What information do you see on this graph that pertains to this one? Well, here is a key one that becomes really useful. When does the derivative equal 0? When does it touch these points? What is that on the curve? That was what we'd call a maximum, right? And we care about maximums. We want to know when we can get the max stuff, the most of something. We want to know that. Now, wait, what about this? Holy cow! Wait, let's put a circle around that. What happens there? That's not a maximum, but that's a minimum. We want to know when we get the minimum amount of things. Sometimes we want little of things. Sometimes we don't want little, so we want to get away from it. So these pieces of information seem kind of useful. Minimums and maximums. I mean, in a vague sense, you could, if you have an equation for things and they have minimums or maximums, how would you solve it? Well, derivatives give you a slope at every point. And if you look, what's the slope at maximums and minimums? What is that slope? Let's just make it m. M equals 0. And what's the slope here? Guess what? M equals 0. So when f prime of x equals 0, we have maxes and mins. Maxes and minimums. Maximums and minimums. So that's an easy application. I'm not going to go into detail just yet, but if you just want to guess, play around with it, Create some functions, try to find their maximums or minimums by taking a derivative, set equals 0, solve for the x value that gets us 0. Usually it's just multiplication, so multiplying by 0 would get you 0. So that is a key thing to look for, but sometimes it isn't. You just have to rearrange things until you solve it. But this is an application. Maximums, minimums. Now, sorry. Well, no, let's move on. So that's one application. Just looking at the curves, you can see that happening. Now, what's one other thing we can look at the curve before I move on? Well, I'm seeing, what's this flat part on here? Well, that's an m equals 0, but that's not a 0 slope here. What is it? What is that at this point? Here, let's put a dotted line because I like those dotted lines. What is happening right there? Well, I kind of see kind of a U shape going on right here. Looks like it's going like this. Then after that, I kind of see a U shape going like this. A parabola shape is a better word here. So it looks like at this point, it's kind of reflecting in the other direction, or what could it be called? Ooh, how about this? The point of inflection. Kind of sounds like reflect. But if you notice, is the point where, well, the second derivative is basically like an acceleration, because the first one would basically be a velocity. And so this would tell you when you stop increasing your speed, in this case we're decreasing the speed because it keeps going negative slope, even though it's 0 at this point, it's still decreasing throughout this whole time. And this point is when it's not increasing or decreasing, and it's going like this again. And it makes more sense if you look at the derivative, this. Now, I would graph the derivative of this, but wouldn't it be kind of straightforward? So this is 0 here. Yeah, it'd be like this. Positive slopes over here, negative slopes over here. So it's kind of a boring derivative, but if you look when it equals 0, whoa, that is our point of inflection. So those are two just graph kind of things we can notice. Now, what else could derivatives tell us? I think I hinted at some of this stuff, or even said it outright, but I'm going to do it again. All right. So let's say we have a function. Let's say it's for speed, and because speed relies on time. There you go, that's a t, not an x. So you plug in time and you get an output. All right, so I'm telling you is that the speed I'm at is 5 times the time that's gone by. Of course, that's only for a certain amount of time. I imagine I wouldn't go 5 times the speed at every point. So let's graph this just to visualize it. So at 0, what will be my velocity? Let's graph velocity on this axis and time on this one. At 0, I'll have a speed of 0. Now I'm slowly going to accelerate this direction. Why did I say accelerate? That's too much of a hint. Let's graph this in black. We're slowly going up. However, it's 5t, so it's just going to be a linear equation. So it's going to look like that. So what can we do with that? Well, velocity, in a sense, is distance over time. And we calculate it by finding a change in distance over a change in time. So if we have an equation for it, we can find the exact distance over time. Let's call it d. Let's make it capital D now for distance, dt. So it's the derivative of a distance equation, all right, with respect to time. So that is what this equation is, 5t. So you plug in a result and you get the speed. So in a sense, change in distance over change in time, that is just speed. So speed is the derivative equation. In a sense, velocity is the derivative. Maybe I should have started with the d function, but let's find out what the d function is based on time. Well, it should just be how far away I am with respect to time. So here we go. How do you get from a derivative to its regular, whatever you want to call it? Well, I'm thinking an integral. What's the integral of that? Well, you increase the power to 2, so you get t squared. And then you divide by 2, and you keep the 5 there. So let's rewrite that. That's 5 halves t squared. However, what I forget, it's not this, because I forgot something. Constant. Although this distance equation works, if you have an equation that looks like this, then an equation that looks like this, you're going the same speed at the same x value, and so the derivative doesn't care about it. But when you care about distance, you have to know that there is some value that you shift up and down by in order to get there. All right? So that is a key concept. So we don't know if we have this kind of situation or this kind of situation. Now, I drew this wrong from the get-go, just because it should be 5 halves t squared, and a positive 5 halves and a t squared gives you a parabola at 0 that increases at a rate of, well, we already know the rate, 5. So now we have a way to calculate distance just from knowing the velocity. So that's applicable, I guess. So, and that's just from starting out with velocity, so I find that pretty useful. But depending on where I am, how much would this change in distance be? On this curve, how much would the change in distance be? I'm drawing on the orange one. I mean to draw on the blue one, but I think you get the concept. If we take 2 points, what's the distance, change in distance? Well, if you calculate change in distance, you're going to subtract one distance from the other distance, so this constant goes away. You just plug in this result, and guess what? That is the definite integral. We have an application for integrals of velocities. It gives you area, doesn't it? Well, the area of velocity is distance. So if you took the integral of this from 0 to 8, so my question here is, if my speed changes at 5 times the time traveled, and I'm traveling from 0 to 8 seconds, let's say this in meters per second. Let's say meters per second. Meters. That's going to be our measurement system. I'm just going to put a box around it. If this was physics that I was talking about, then I would emphasize it after everything, but we're not. We're just talking about math applications. So 0 to 8, what could we do? So we have 5t. And we care about t when we take the integral. So it's dt. You could also think of it as that tiny area. So the area of this function should be this change on the curve, and I should draw it on the blue curve. And so we're going from 0 on this equation to 8 on here. So we're just trying to find this length. And if you drew the same curve moved up, it's still going to be the same length. Oh, now it's all black. Whatever. So what will this tell us? So if we're increasing at a rate of 5 times the time that it has been elapsed since the beginning, which we'll just say is 0, then we get 5 halves t squared, plug in 8. So 8 squared is 64. 64 divided by 2 is 32. 32 times 5 is half of 320. 320 divided by 2 is 160. Let's just check that. So 5 halves, that's kind of fast. 64, so that's equal to 5 times 32, because 64 divided by 2 is 32. And 5 is the same as 10 divided by 2 times 32. So 10 times 32 is 320. 320 divided by 2 is 160. Yep, checks out. And then we subtract the value at 0. What is the value at 0? 0 squared is 0. 0 times 5 is 0. 0 divided by 2 is 0. 0 plus a constant that goes away because there's a constant here technically. And then we subtract 0 minus a constant. Guess what? The constants go away. So we get 160 minus 0. So we went 160 meters in 8 seconds. That's actually ridiculous, I would say. But still, application. And that's just the area. It doesn't look like the area because we're talking about distance, not area. So how could it be the area of a curve? Crazy stuff. Then you could take another derivative and get acceleration equals derivative of that is just 5. So it's always accelerating at 5. Well, what is the units? If we're doing meters per second, then this is meters per second squared because we're dividing, remember, this looks like this, d squared over dt squared of the function. That would be the second derivative, so it's an arrow, not equals. All right, that's true. And so we get our time squared, the second squared. So that is units of acceleration. If you didn't know that, well, you just proved it using derivatives. All right, what else can we do? There has to be more. Well, there is. How about this? Just an idea for integrals, all right? So we take a curve. Well, I know how to figure out. So it seems like we're starting everything we know with our knowledge of lines, right? How do you figure out the distance of here to here on a line? Well, you would square this distance, and square root them together. Because there's a, b, and this c. And a squared plus b squared equals c squared, or c equals a squared, square root of a squared plus b squared. So you take the change in x and the change in y and do it, and you get a c. Well, if we have a curve, we have a bunch of infinitely small triangles. So let's set them up. Let's set up a random example like this, all right? Remember how we did like small areas and kind of thing? Well, here we go. We have a tiny change in y, all right? That is a change in y. It's just we're talking about in calculus terms, so no longer change in y, but we're using dy. All right? So that's the differential of y, however you want to think of it, whatever. This is x. This is x direction, right? So let's call this length, all right? So let's make it L, curly L, dl. So what does dl equal to? Well, dl squared equals dx squared plus dy squared. Okay. That might be useful. But how do you figure out this whole length? That's only one tiny length. Well, you have to add them up, right? But there's so many of them, you have to add them up infinite times. That's the key concept. That's an integral. Integral of dl has to be the whole length from a to b. Let's call this a, and let's call this b. We're actually going to use a and b here. Not alpha and beta, but whatever. So this is crazy. An integral is basically a distance. Wait a minute. Okay, no, I'm not even going to get into that. Let's just finish up here. So dl, let's replace dl because we don't really know how L changes. But we do know how dx and dy kind of change because they're related by each other to each other. So let's rewrite this. So how do you get rid of the squared? Scribble it out, square root it. Technically be plus or minus, but distance is only positive, so we can ignore that. So dl is now dx squared dy squared from a to b still. Well, I don't know. I don't know how to solve that, to be honest. So we have to rewrite it. Because usually we have like something we can care about. Some variable we can worry about. But here. Let's factor our dx squared. So let's put dx. If we factor our dx squared, square root of dx squared is just dx. And then you get 1, because 1 over dx squared, well, dx squared divided by dx squared is 1. Then there wasn't dx squared, so we had to kind of manufacture into the equation. So we have to divide by dx squared in order to get it out of the equation. So we get dy over dx, and both of them are squared, so let's just factor out squared. And this is from a to b. And guess what? That is the length from a to b. I think this is insane that we can calculate lengths that seem impossible with this. Of course, it turns out that lots of equations aren't the prettiest when doing this, but if you look, what is this? This is the derivative. So if we calculate the derivative and plug it in and then take the integral of it, of all this stuff plugged in, then we can calculate the area of a curve. So if we have x squared, what is the length of x squared from a to b? Well, the length from x squared is... So what's the derivative of x squared? That's 2x, so that becomes, when you square it, because we have to square the derivative, so it's 2x, so 2 times x, 2x times 2x is 4x squared. All right. I actually don't know how to simplify this at the moment. I mean, this is actually something you could do with trig. But just to give you an idea, you can plug this in a calculator. You can also estimate it. And estimating is sometimes good enough. But this is awesome. We have a way to calculate exact lengths. And lengths can become surface area, and areas, which we learned about, can become area. So many applications. And just to finish off, just give you an idea of things that we take integrals of. If you have lots of our equations that we learn in physics, we only have like a dot. We only talk about dots. So you have like an m times g. So that would be like the force of gravity, right? Let's just straight gravity. Gravity. All right. And then, no, there's other forces. I'm not going to go into that. But what if you had a whole block that wasn't consistent area? I mean, consistent density or anything, really. Well, if you had a function for the density, guess what? If you took the integral for every point, well, I guess we'd actually take the addition of every point, infinitely many points, and we're going to find every mass times gravity. Well, gravity is just the constant 9.8 if you've learned that. If you haven't, don't worry. That's just gravity on Earth, meters per second squared. All right, so we can plug that in, factor it out, so you get 9.8, meters squared, whatever. And this is an infinite summation of m. Since the mass changes at different points, it might be different masses. But how do we find it? Guess what? Integral. The integral of m. And then I guess you do like a dx. And then you also take another integral, dy, because you want to see how it changes in the x direction and the y direction, up and down. So you have 2 dimensions. And then if you have a 3D object, guess what? dz. Take another integral, whatever. You can find exact masses using integrals. So now you can actually use our physics equations accurately. You don't have to just say, okay, imagine this is just one dot. I mean, usually that's a nice approximation, but it's often not good enough. So these are the ideas of calculus. Technically, 3D volumes. I mean, if you take an integral 3 times, you're basically finding a volume. And I imagine you know pretty well how to find some volumes, so technically you already know some of these mass equations. Either way, list goes on and on. This is just a really overview of ideas that will show up. And there's a ton more. So what did we say? We said maximum, minimums, point of inflection. What did we say here? Areas of velocity and derivatives of velocity. So we just investigated what rates have to do with derivatives. And then here we kind of investigated the power of the integral. Thanks for watching.